The greatest common factor of two numbers is the largest number that can be evenly divided by both numbers. For example, the greatest common factor of 30 and 18 is 6. If I break 30 into its prime factorization, that would be 2 times 3 times 5. And 18 into its prime factorization is 2 times 3 times 3. I have a 2 here and a 2 here, a 3 here and a 3 here. What's left is a 5 and a 3. Those don't match, so I can leave them. 2 and 3 are the factors that match. 2 times 3 equals 6 is the greatest common factor. What's the greatest common factor between 72 and 48? 72 equals 2 times 2 times 2 times 3 times 3. 48 equals 2 times 2 times 2 times 2 times 3. Where do they match? 2, 2, 2, 3. The greatest common factor is 2 times 2 times 2 times 3 equals 24. It works the same way with polynomials. If I have 4x plus 16, the greatest common factor of 4x and 16 is 4. I can factor out the 4, and then what's left remains in the parentheses. 4 times x plus 4. And this is the first step in factoring polynomials. I'm on page 119 in the packet. Let's work through a few of these to get the hang of it. If I multiply 3x times something, I'm going to get 3x squared minus 24x. What could this be? The first term is 3x squared. I need to multiply something by 3x to get 3x squared. So this must be x. Then I have to multiply something by 3x and get negative 24x. That must be negative 8. We have 3x times 3x minus 8 equals 3x squared minus 24. And you can check using the distributive property that this is so. Now I want to multiply something by 5m plus 6 in order to get 35m cubed plus 42m squared. 35 divided by 5 is 7, and I need to turn this m into an m cubed. So what if I multiply by 7m squared? What would happen? I get 35m cubed here, just like I wanted, and 6 times 7m squared is 42m squared, which is exactly what I want. The answer here is 7m squared. You can try numbers 3 and 4 on your own, but the answers will be 2y squared minus 3 and negative 2x. Number 5. X plus 3 times something equals x plus 3 times 6x minus x plus 3 times 5. Well, notice both of these things are multiplied by the x plus 3. We can factor out the x plus 3, and we're left with 6x minus 5. For part B, we need to find the greatest common factor and pull it out. The greatest common factor of 10 and 4 is 2. That means the greatest common factor between 10x cubed and 4x squared is 2x squared, right? Because whatever x is, both of these have an x squared attached to them. So it can be factored out. Now I have 2x squared times something is 10x cubed minus 4x squared. 2x squared times 5x equals 10x cubed, and then I need negative 4x squared, and that's minus 2. That's the factorization I want. 2. 9n to the fourth minus 18n cubed plus 27n squared. Okay, first of all, I can see that all these have an n squared in them, right? I can pull out n squared. What is the greatest common factor of 9, negative 18, and 27? 9 goes into each, so I can factor out 9n squared. And that gives me n squared minus 2n plus 3. This last one is in a somewhat different form. We have v times 2v plus 1 plus 4 times 2v plus 1. 2v plus 1 is the greatest common factor of this term and this term. I can factor out the 2v plus 1, and that leaves me with v plus 4. Now we have to factor a trinomial where there are no common factors between the terms. Today, we'll look at the situation where the leading coefficient is 1. This is a version of the AC method, which we'll cover next week and is more general. When we have a trinomial with leading coefficient 1, what we do is look at all the factors of the constant term and find the pair that sum up to the middle term, the one that's attached to x. In this case, our constant term is 16, and all the factors of 16 are listed here. There's also going to be 2 times 8, negative 2 times negative 8, and negative 4 times negative 4. The goal is to find the pair that sums to 10. 1 and 16 sum to 17. Those don't work. Negative 1 times negative 16 equals 16, but they sum to negative 17, so they won't work either. 2 times 8 is 16, and 2 plus 8 is 10. That's it. That's the one we need. There's never any ambiguity here. If one of these pairs fits, it will be the only one. This is 8, but we don't need that. My factorization will then be x plus 2 times x plus 8. And you can see that if we FOIL this, we get x squared plus 8x plus 2x plus 16, and that's x squared plus 10x plus 16. That's what we're doing with this table. We're finding the factors that we can put through the FOIL process to get the trinomial. If we took negative 1 and negative 16, for example, that would be x minus 1 times x minus 16, which is x squared minus 16x minus x plus 16, x squared minus 17x plus 16. And that's why it doesn't work. You see, this factorization gives us the constant term we want, but not the x term. You can shorten the search for factors if you look at the possible signs you would need. Let's say you have a trinomial ax squared plus bx plus c. It could factor into x plus m times x plus n, because that gives us x squared plus mx plus nx plus mn, and this term is positive and this term is positive. But negative times negative is positive, so could it also be x minus m times x minus n? No, because then we have x squared minus mx minus nx plus mn. This middle term is negative, not positive like we want. So the factors for this form could only be plus and plus. Similarly, if this term is positive and this term is negative, it must be in the form x minus m times x minus n. The only way c can be negative is if you multiply a negative times a positive. This would have to be in the form x minus m times x plus n, or maybe x plus m times x minus n. But say we have this one, x minus m, x plus n. Then you'll wind up with this one if n is bigger, if the positive term is bigger, and this one if the negative term is bigger.